In this tutorial, we'll model a parametric hip joint implant in Nodi. First, in an external CAD tool, we build the loft form that matches the actual bone data. To start, we drop an import geometry node and load the femur surface mesh. To wrap the bone in a lattice, we feed the surface into a dual surface cell map and an implicit beam, with the cell type set to cubic. Every edge becomes a strut. To build the inner spine, we import the centerline curve, run it through Carve, and reparameterize. Convert it with Carve. To Implicit, and use Implicit Thicken to give it a solid radius. To mark where the lattice begins and ends along the stem, we drop 2. Evaluate curve nodes driven by number sliders at roughly 0.5 and 0.95. Each point feeds a plane normal node, building a plane perpendicular to the curve. These planes will later clip the region where the lattice is applied, so we orient them to face each other. To grade the lattice density from sparse to dense, we add 2 implicit ramps and an implicit intersection. Each ramp creates a scalar field that fades as you move away from its plane. To expose the controls, we lay out 4 number nodes and label them start value, start distance, and end distance. We wire them into both ramps. These 4 sliders now drive the entire density gradient. To clip the lattice region, we add 2 implicit plane nodes built from the perpendicular planes. To create the solid shell, we run the femur mesh through mesh to implicit, then implicit offset, thickening the surface inward. Now we assemble the booleans. Implicit union joins the thickened shell with the lattice. Implicit intersection clips the result against the ramp field, so the lattice only appears in the middle band. To carve out the inner cavity, we add an implicit difference. With these booleans in place, the entire stem updates parametrically. To inspect the result, we add a BBox and an implicit slice display, driven by a number slider. The heat map reveals the signed distance field at any cross-section. To set up the femoral head, we use construct vector for the sample location, feed it into evaluate surface on the cut surface, and read back the point and its normal. To build the cut where the ball meets the stem, we pass that through plane normal, FFlip, and implicit plane. To merge the 2 branches, we flatten both data trees and combine them with a final implicit intersection. Finally, hide the pelvis mesh. The finished implant is revealed.